Hello friends, in the last lecture we learnt the two categories of bistable devices, the latch and the flip flop. The basic difference between latches and flip flops is the way in which they are changed from one state to the other. The flip flop is a basic building block for counters, registers and other sequential control logic and is used in certain types of memories. In today's lecture, we shall be talking about flip flops operating characteristics, which include the performance, operating requirements and limitations of flip flops. Generally, these applications are applicable to all CMOS and TTL flip flops and are found on the data sheet for the device. Then we shall talk about flip flop applications and the astable multivibrators. Propagation delay time. A propagation delay time is the interval of time required after an input signal has been applied for the resulting output change to occur. Four categories of propagation delay times are important in the operation of a flip flop. The first one is propagation delay TPLH as measured from the triggering edge of the clock pulse to the low to high transition of the output. The second is the propagation delay TPHL illustrated in figure B and is measured from the triggering edge of the clock pulse to the high to low transition of the output. Third is propagation delay TPLH as measured from the leading edge of the preset input to the low to high transition of the output. This delay is illustrated in part A of the figure for an active low preset input. Fourth, propagation delay TPHL as measured from the leading edge of the clear input to the high to low transition of the output. This delay is illustrated in part B of figure for an active low clear input. Setup time. The setup time Ts is the minimum interval required for the logic levels to be maintained constantly on the inputs prior to the triggering edge of the clock pulse in order for the levels to be reliably clocked into the flip flop. This interval is illustrated in figure for a D flip flop. Hold time. The hold time Th is the minimum interval required for the logic levels to remain on the inputs after the triggering edge of the clock pulse in order for the levels to be reliably clocked into the flip flop. This is illustrated in figure for a D flip flop. Maximum clock frequency. The maximum clock frequency is the highest rate at which a flip flop can be reliably triggered. At clock frequencies above the maximum, the flip flop would be unable to respond quickly enough and its operation would be impaired. Pulse width. Minimum pulse widths for reliable operation are usually specified by the manufacturer for the clock, preset and clear inputs. Typically, the clock is specified by its minimum high time and its minimum low time. Power dissipation. The power dissipation of any digital circuit is the total power consumption of the device. For example, if the flip flop operates on a plus 5 volt DC source and draws 5 milliamperes of current, the power dissipation is VCC into ICC and is equal to 5 volts into 5 milliamperes and equals 25 milliwatt. The power dissipation is very important in most applications in which the capacity of the DC supply is a concern. As an example, let us assume that you have a digital system that requires a total of 10 flip-flops and each flip-flop dissipates 25 milliwatt of power. The total power requirement is 10 into 25 millivolt and is equal to 0.25 watt. This tells you the output capacity required of the DC supply. If the flip-flops operate on plus 5 volt DC, then the amount of current that the supply must provide is equal to 250 milliwatt divided by 5 volts and is equal to 50 milliamperes. You must use a plus 5 volt DC supply that is capable of providing at least 50 milliamperes of current. Flip-flop applications. Here we shall be discussing 3 general applications of flip-flops to give you an idea of how they can be used, but flip-flop applications in counters and registers shall be covered in detail in later lectures. After completing this section, you should be able to discuss the applications of flip-flops in data storage, describe how flip-flops are used for frequency division and explain how flip-flops are used in basic counter applications. Parallel data storage. A common requirement in digital systems is to store several bits of data from parallel lines simultaneously in a group of flip-flops. This operation is illustrated in figure using 4 flip-flops. Each of the 4 parallel data lines is connected to the D input of the flip-flop. The clock inputs of the flip-flops are connected together so that each flip-flop is triggered by the same clock pulse. In this example, positive edge triggered flip-flops are used, so the data on the D inputs are stored simultaneously by the flip-flops on the positive edge of the clock, as indicated in the timing diagram. Also, the asynchronous reset inputs are connected to a common clear line, which initially resets all the flip-flops. This group of 4 flip-flops is an example of a basic register used for data storage. In digital systems, data are normally stored in groups of bits that represent numbers, codes, or other information. Frequency division. Another application of a flip-flop is dividing or reducing the frequency of a periodic waveform. When a pulse waveform is applied to the clock input of a JK flip-flop that is connected to toggle, the Q output is a square wave with 1/2 the frequency of the clock input. Thus, a single flip-flop can be applied as a divide by 2 device. As you can see, the flip-flop changes state on each triggering clock edge. This results in an output which changes at half the frequency of the clock waveform. Further division of a clock frequency can be achieved by using the output of one flip-flop as the clock input to the second flip-flop. The frequency of the QA output is divided by 2 by the flip-flop B. The QB output is therefore 1/4 the frequency of the original clock input. By connecting flip-flops in this way, a frequency division of 2 to the power n is achieved, where N is the number of flip-flops. For example, 3 flip-flops divide the clock frequency by 2 to the power 3, and that is equal to 8. 4 flip-flops divide the clock frequency by 2 to the power 4, and so on. Counting. Another important application of flip-flops is in digital counters. The flip-flops are negative edge triggered JKs. Both flip-flops are initially reset. Flip-flop A toggles on the negative going transition of each clock pulse. The Q output of flip-flop A clocks flip-flop B. So, each time QA makes a high to low transition, flip-flop B toggles. The resulting QA and QB waveforms are shown in the figure. Observe the sequence of QA and QB prior to clock pulse 1. QA is equal to 0 and QB is equal to 0. After clock pulse 1, QA is equal to 1 and QB is equal to 0. After clock pulse 2, QA is equal to 0 and QB is equal to 1. And after clock pulse 3, QA is equal to 1 and QB is equal to 1 as well. If we take QA as the least significant bit, a 2-bit sequence is produced as the flip-flops are clocked. The binary sequence repeats every 4 clock pulses as shown. Thus, the flip-flops are counting in sequence from 0 to 3, that is 0 0, 0 1, 1 0 and 1 1, and then recycling back to 0 to begin the sequence again. Monostable multivibrator. The monostable multivibrator, also called the one-shot, is a device with only one stable state. This device is normally in its stable state and will change to its unstable state only when triggered. Once it is triggered, the one-shot remains in its unstable state for a predetermined length of time and then automatically returns to its stable state. The time that the device stays in its unstable state determines the pulse width of its output. Figure here shows a basic one-shot or the monostable multivibrator that is composed of a logic gate and an inverter. When a pulse is applied to the trigger input, the output of gate G1 goes low. This high to low transition is coupled through the capacitor to the input of inverter G2. The apparent low on G2 makes its output go high. The high is connected back into G1, keeping its output low. Up to this point, the trigger pulse has caused the output of the one shot Q to go high. The capacitor immediately begins to charge through R towards the high voltage level. The rate at which it charges is determined by the RC time constant. When the capacitor charges to a certain level, which appears as the high to G2, the output goes back low. To summarize, the output of inverter G2 goes high in response to the trigger input. It remains high for a time set by the RC time constant. At the end of this time, it goes low. A single narrow trigger pulse produces a single output pulse whose time duration is controlled by the RC time constant. A typical one-shot logic symbol is shown in part A of the figure, and the same symbol with an external R and C is shown in part B. The two basic types of IC one-shots are non-triggerable and retriggerable. A non-retriggerable one-shot will not respond to any additional trigger pulses from the time it is triggered into its unstable state until it returns to its stable state. In other words, it will ignore any trigger pulses occurring before it times out. The time that the one shot remains in its unstable state is the pulse width of the output. Figure here shows the non-retriggerable one shot being triggered at intervals greater than its pulse width and at intervals less than the pulse width. Notice that in the second case, the additional pulses are ignored. A retriggerable one shot can be triggered before it times out. The result of retriggering is an extension of the pulse width as illustrated in figure. The 74121 is an example of a non-retriggerable IC one shot. It has provisions for external R and C as shown in figure. The inputs labeled A1, A2 and B are gated trigger inputs. The R internal input connects to a 2 kilo ohm internal timing resistor. A typical pulse width of 30 nanoseconds is produced when no external timing components are used and the internal timing resistor is connected to VCC. The pulse width can be set anywhere between about 30 nanosecond and 28 second by the use of external components. Part B of figure shows the configuration using the internal resistor and external capacitor. Part C shows the configuration using an external resistor and an external capacitor. The output pulse width is set by the value of the resistor and the capacitor according to the following formula. TW is equal to 0.7 RC external, where R is either R internal or R external. When R is in kilo ohm and C external is in picofarads, the output pulse width TW is in nanoseconds. The 74LS122 is an example of a retriggerable IC one shot with a clear input. It also has provisions for external R and C as shown. The inputs labeled A1, A2, B1 and B2 are the gated trigger inputs. A minimum pulse width of approximately 45 nanoseconds is obtained with no external components. Wider pulse widths are achieved by using external components. A general formula for calculating the values of these components for a specified pulse width is TW is equal to 0.32 RC external into 1 plus 0.7 over R, where 0.32 is a constant determined by the particular type of one shot. R is in kilo ohm and is either the internal or the external resistor. C external is in picofarad and TW is in nanoseconds. The internal resistance is 10 kilo ohm and can be used instead of an external resistor. An application. One practical one-shot application is a sequential timer that can be used to illuminate a series of lights. This type of circuit can be used, for example, in a lane change directional indicator for highway construction projects or in sequential turn signals on automobiles. Figure here shows 374 LS122 one-shots connected as a sequential timer. This particular circuit produces a sequence of 3 ones pulses. The first one shot is triggered by a switch closure or a low frequency pulse input producing a ones output pulse. When the first one shot times out and the ones pulse goes low, the second one shot is triggered, also producing a ones output pulse. When this second pulse goes low, the third one shot is triggered and the third ones pulse is produced. So friends, that brings us to the end of our discussion in this lecture, and therefore we sum up. In this lecture, we learnt that astable multivibrators have no stable state and are used as oscillators to generate timing waveforms in digital systems. Setup time is the time required for input data to be present before the triggering edge of the clock pulse. Hold time is the time required for data to remain on the inputs after the triggering edge of the clock pulse. A group of data storage flip-flops is a register. A non-triggerable one shot times out before it can respond to another trigger input. A retriggerable one shot responds to each trigger input. Pulse width is set with external R and C components. So, that is it for today. See you in the next lecture with more on digital circuits. Thank you very much.